rush. We simply take these 20 minutes.
Just here tells me that the meeting is recorded. Okay, so welcome to this afternoon session, which I will start here. And well, we have here in Wrocław since the beginning of epidemics quite a lot of activities in forecasting and analyzing with the help of relatively complex agent-based models, the epidemic progression, mainly in Poland, but also with some colleagues in Germany, which are also in the MOCOS group, that's our group is called, involved. And because it's a talk about in a conference on mathematics in industry, I would not just too much focus on simulation results or the full details of the agent-based model, but try to make a point on the mathematical side as well. And so let me start with a few general remarks. I quickly go through, and just now I have to, okay, this is now working, okay. So there's an explosion of models since the COVID epidemics. I mean, never seen in the history of epidemic models, I would say. And we have now for Germany and Poland about 40 teams which do weekly predictions, right? They are on the European Forecast Hub and previously on the German-Polish Forecast Hub. And all kinds of models. You see, they have times where most of the models fail, especially when it comes about when the turn of the peak is going. This is the second wave here, and you see how largely the models went off in 4 weeks predictions. And then when it stabilizes, then the predictions become better. So, and actually, it's not a clear favorite type of model which does the best predictions, right? There are models which are, well, the classical, most of the models are ordinary differential equations model of the type as they are since 100 years in use in epidemics. Well, the first one around the beginning of the 20th century for malaria, and with a little bit stochastic modifications. Then you have, or maybe partial differential equation, it's all relatively rare. Then you have, due to the increased computer power, a lot of agent-based model, but they are still the minorities because you have to put more, well, it's more computational powers you need and so on. And they are more difficult to analyze. And then you still have, of course, purely statistical timeline, series predictions, and so on. And forecasting is not just the only reason you do modeling. You try also to understand the impact of certain countermeasures, say, or intervention measures on the epidemics, and what really are the driving factors and how the epidemics depend on certain key parameters, medical, social ones, and so on. That is somehow in the focus of understanding epidemics with the help of models. And here, purely statistical prediction models are good for predictions, but not much for anything else, because you don't have much dynamical insight into epidemics. Good, so when you do agent-based model, you can start actually at different levels. And here is the main difference. Some people start really moving people around, and they have a certain time, they are in close proximity, and then they somehow simulate the times, and depending on the times and the state of the infection you have a transmission probability, and then you get all the contacts and things linked. So in a very microscopic level, I will here somehow deal with agent-based model, which starts a little bit upper, which somehow have as a starting point the individual number of infections you generate, right? So already on this network level, which somehow has accumulated what was causing the network, okay? And so essentially you have a graph structure representing contacts between individuals. This can everything depend on time because we have restrictions ongoing and going away. And then you have states of infection and transmission probabilities between those. So you have a time aspect still, how long it takes somebody to infect. And it's actually convenient to look only at the infectious links, right? Which are, of course, a result of an underlying link structure between contacts. But what really matters is just the number of potentially infectious link. So imagine every person is at some time infectious, how many of his contacts he would infect, and that you represent as a so-called infection graph. Good. How to specify a network, the most convenient way, also from a mathematical point of view, is by so-called contact kernels. So you have features assigned to the individual's age, gender, the profession, the working habits, social activities, and so on. And also the state of the infection, of course, and then depend how long, for instance, a person is infectious, and then depending on that, you generate edges defined via a function which depends only on the states of the individuals which are under consideration, such kernel functions, and they define the transmission, the network of infectious contacts actually. And it could all be time and state, they are all time and state dependent, of course. And I would like to view the epidemics actually as a percolation process. So a percolation process, percolation theory has a long history, and it's somehow you have a network and certain edges are counting as open. These are the infectious edges and other ones not. And the question is, when you have a situation that you have a large connected component, this corresponds to an overcritical epidemics. And if you have everything partitions into small disconnected component, an epidemic will slowly die out. So these are classical question studies mostly on lattices previously, but also already in the 1960s on so-called random networks. And the pioneering people here were Erdos and Rainey, and this is somehow showing with a Poisson individual reproduction number, so number of secondary cases you generate, how the network structure changes if you go from a little bit below reproduction number 1 to a little bit above reproduction number 1. And you see the emergence of what's called a so-called giant component. And these are objects which are accessible to mathematical study, understanding this phase transition actually between subcritical, overcritical, and how the size of this large connected component, which finally defines how many people will get infected, can be computed. The pioneers here were Alfred Rainey and Paul Erdos, famous mathematicians, and they somehow started the subject of random graph theory. Now, a very, very large extension, and actually somehow the mathematical framework in which we are working came in 2005 with the work of Bollobas Janson and Riordan on heterogeneous random graphs, where they took the idea of Erdos and Rainey that edges are still independent, but not identically distributed. So they depend on the feature vectors of individuals. And now the feature vector can be a large things of things. Everything you're interested in and you think have an impact on the network connectivity and on the individual number of secondary cases finally an individual generates, that you put into features of the individual and distribute it according to a certain law. Okay, and then the probability that I infects J if I is infected is defined by such a kernel, and you normalize it to get sparse graphs. So the degree or the secondary number cases is bounded. So this is the setting in which we do things here. And the features you actually add are socioeconomic properties, especially also the time being infectious, which is of course determined by incubation time, and you distinguish it also between in-household and out-household. Then all the countermeasures, whether you are tested or not, or you are quarantined, that you can a priori assign actually as features to the individuals. The contact tracing is more difficult. I will not have no time to speak actually about this, even if I was in the abstract mentioning this. Good. So the local structure, most importantly, as I already said, once you have these kernel functions, you get the expected number of secondary cases, which depend now on the individual's features. And this is this lambda of X here, and you just integrate over all the possible contacts you could have and somehow up. Okay, so your individual reproduction number is Poisson distributed, but not homogeneous. Every individual might have a different Poisson distribution in terms of secondary number of cases he generates. And the important mathematical object is a so-called transfer operator, which somehow defines the local network structure. So this is defined in that way. If you have only a finite number of types, you can think of a matrix given by this contact, by this kernel function, okay? And the important theorem here is proved by Bollobas and Janson Riordan is if the norm, and if you have symmetric edges, it's just the L2 norm, but in non-symmetric case, it's a spectral norm. If this norm of this operator is larger one, you have an epidemic outbreak, you are overcritical. And if it's less than one, you have a subcritical epidemics, which goes extinct. And most of the interesting epidemiological will depend only on this norm, which you can interpret as the asymptotic reproduction number as well. Now, and then you have, in analogy to the Erdos setting, also a formula for the size of the final, how many people get infected. It's a nonlinear integral equation here, and it's the rho of X you can interpret as the probability if an individual of type X gets infected, that the local epidemics starting with this individual will actually really not die out quickly, but will grow, right? This is the so-called survival probability of the associated local branching process, because the local network graph structure is actually tree-like here. Okay. Now, important extensions are needed, and foremost is the households. And I will say a few words about the household. You will see here over all the time of the epidemics, we have approximately 30% of the infections going on in the households. So you have to take care of this. And it's when you go somehow from individuals to households, and that is actually the right thing to view the epidemics as an epidemics between households, you have something appears which actually can make the things more difficult in the fight against the epidemics. So you now merge individuals which live together, and you see that even if there is no targeted or preferential attachment on the individual side, households of size K have, so the probability that a household with size K and another household with size M have a link is proportional to the product of the household sizes. So a 3 and a 4 household have a probability 12 times higher to have a contact than a single household. That's called a preferential attachment scheme, and it gives rise to a so-called multiplicative kernel. And now, assuming that not everybody in the household get infected, and you have, I just make for didactical reasons here this relatively transparent setting. So the out household contact structure is Poisson with a parameter C, like in Erdos setting. And inside the household, you have an attack rate, which means the fraction of household members once an infection comes in, which gets infected. And taking this into account, you can now translate the graph structure on the individual to a graph structure on a household. And you get a kernel, which is pretty much like a product kernel, where X and Y are the household sizes. And now this defines a so-called rank 1 operator. And you can explicitly compute the spectral norm here for this. And this is given here in equation 4. So it takes into account the household size distribution. And you see that the spectral norm depends on this out-household number of contacts per individual, that's given by C, the mean number, but also on the ratio between the second moment and the expectation of the household size distribution. So if you have a high second moment, it's somehow like it has a catalytic effect on the epidemic, and it enlarges the spectral radius, and you have to bring the spectral radius below 1 to stop the epidemics. So here is for Poland, for instance, the distribution of the second moment on a very fine scale, 10 by 10 kilometers printed. And you see you have some regions, the red ones, which have very high second moments, and that are somehow structurally vulnerable regions for the epidemics. And indeed, these are in the history now over the epidemics, the regions where you have very, very high dynamics and higher number than in our regions. Now, in our application, let's see what happens if you let children, for instance, stay at home and they don't go into school. So I will not go through the formulas here. I just show you that you can do the math if you assume that a certain fraction of children, say between 2 years and 14 years, could either stay home or go to school. So let's see how strong the effect if you want to let them stay home. And this fraction is B, say. In Germany, it's about 10%. In Poland, it's about 15% of the population. Now, you define a kernel which takes into account that part of the people in the household not going out, that the children, and you assume, of course, children are never in single households living as at least one adult in the household. And then you get this contact kernel for the households, including now children which stay at home, don't go out, and you can compute so-called the children spectral norm of this operator. And then you can see how much the effect is if you leave the children home. And this reduction effect on the spectral norm doesn't depend on this, coefficient C here, which somehow is the out-household number. But the reduction is uniform over all what is the imposed restriction outside. And in Poland, it's actually 23% of restriction given the second moment and the first moment of the household size distribution. And in Germany, you get still a 16% reduction of the spectral norm under the assumption now that the household attack rate is 20%, which corresponds somehow to the British variant. Right, so these are quite interesting, not simulation results, the theoretical results which you can achieve here. Another application is vaccination, how large of the population you have to vaccinate, assuming for simplicity uniform vaccination in the population. Again, you can translate it in a contact kernel between the households. You look now only for those who can get infected. And you see how much the spectral norm is reduced with the vaccination in this little picture here. There are 3 graphs. The green one is Germany. The black one is, which is close to the green one, is Poland with its different second moments of household size distribution. And the other line is for a higher in-household attack rate than we have at the moment, but there might be variants which actually do this. You see that the target value to reach somehow immunity or subcriticality would be close to 80% for both Germany and Poland. The reason for that is as more you vaccinate, as more somehow reduce effectively the household size. And if you come to the phase transition, more or less it's the number of household sizes in terms of how many susceptibles you still have there goes to 1. So you essentially they become equivalent in terms of having only single households still, because the rest of the members are vaccinated. So it's 80%, which we get here from this computation somehow. Okay, another aspect is do you have in a natural way directed graph instead of the symmetric ones in Bollobas Janson Riordan. And there is an extension partially worked out by ourselves, also by our groups, for non-symmetric, for directed networks. I will just say that there is one. And you have now in this context 2 actually spreading processes. One goes forward in time, but you could also view the epidemics from a person who is not yet infected as an incoming. So you look somehow backwards in time, so against the direction of the epidemic flow. And this backward dynamics corresponds to a process which is actually the adjoint process, defined by a transfer operator, which is the adjoint, so they have the same phase transition. And looking at the dynamics somehow from a backward in time perspective is actually useful, because you see the backward process is very often simpler. And I just want to illustrate it here with the super spreading cases. So if I have a population where, I forget now about the household for a moment, I have a population where I have very, very large heavy tails for the individual reproduction number. So some people infect really a lot. In that case, but they are not targeted. So the contact kernel, the people you infect, is just given by C times an individual parameter, which is heavy tail distributed in the population. And you see what matters, the probability that the person eventually get infected doesn't depend on its type. So how many he will get infect. And that means that for the phase transition and also for the size of the people who eventually get infected, only the mean value of this heavy tail distribution matters, but not the shape of the distribution itself, right? So it actually doesn't depend whether it's heavy tail, whatever distribution you have on secondary cases, as long as they are not targeted into something, then the infections you produce, only the mean value matter. And that is actually a useful thing. We see that a lot of things, when you put too much differentiation, for instance, in some of the agent-based model, they actually have, they enter into epidemics dynamic only by the mean values. And that you can understand looking at this mathematical structure. Good. A last word about timing. This is structure, was everything I said before was about structural properties. So not taking into account how long it takes to infect somebody. If you do this, if you want to really speak about real-time evolution, you have to assign so-called generation times. That means a person which infects another person, how long it takes from the infection of the first person that the second person gets infected, so-called travel times. And that brings you in what is called first passage percolation, where you go from one node to another node via a so-called open edge or infectious edge, but it takes some time. And now you can describe the epidemics in real time. And you can actually see how much is depending on the distribution of this timing, how the epidemics, how fast the epidemics will grow in terms of the actually incidences. And here is a classical result. So if you have a single type epidemics, say, but with individual heterogeneity in the reproduction number, then the local epidemics is a branching process of Golden-Watson type. And the growth rate then depends on the distribution of this so-called generation intervals and the mean reproduction number here. And essentially you have to solve m times the Laplace transformation of this generation times interval has to be 1. You solve it and then you get the so-called Malthusian growth parameter. And this depends very much on the shape and on the type of the distribution of the generation, but at least there is a closed formula to compute this. And this extends to multi-type settings, even to infinite type, which is some of the things we did here. And you get an equation where you somehow have this norm of this operator, which I previously was speaking about. You have to multiply still with the Laplace transform now of eventually individual depending generation times, a type depending generation times in. You look for the solution of this norm operator norm equal to 1, and that defines you the Malthusian parameter. Once you have this, you can...
excuse me,
yes?
the time is, I don't know how much you still have, but we're running a bit out of time.
Okay, so tell me how much I still have.
2 minutes.
All right, good. So let me still here just quote one theoretical result. it's actually possible to say precisely how the timing, if the epidemic starts at a given node, how long it takes that another node, a randomly chosen node, gets infected. And this has a universal shape. And this is a relatively non-trivial mathematical theorem. So there is somehow a way how to, there's a kind of universality in the shape of the epidemics, how it grows, which depends, of course, on some aspects, but how it depends on this is relatively universal. And so I just wanted to mention it, and it had certain consequences. I will maybe not able to speak here. So let me come to, at the end, still show a few pictures. Here is the epidemics somehow independence over the phase space as a reduction of contacts, efficiency of contact tracing, and you see there is a sharp phase transition between overcritical and subcritical. So you can do this now on the country level, and you can try to specify somehow the parameters which are really now fitting to the present epidemics. We have in Poland here, we had at least for some time access to individual linked patient data sets, which we use and estimate certain things out of that. And that is somehow what you then would do if you really want to make also good forecasts, specifying your parameter sets. But what are important parameter set actually comes from the theoretical considerations I mentioned before. And then you still have maybe contact matrices on age here. So these are the data you plug in, not only we. And then you get a more narrow regime eventually where to localize the epidemics, and you use this for the predictions. And so as a summary of the math, essentially are two numbers which determine in an agent-based model, which amount to, everything amounts to two numbers. The one is the spectral norm, and the other one is this Malthusian parameters, which involves Laplace transform of the generation times. But these are the two things which finally make the prediction, how good you estimate it, and then of course comes a little bit else if you for the saturation and things like that. But this is really the two key numbers you have to understand well, and how they depend on properties you impose in your society. So thank you very much. There is a page with some references, and we have here the people, well, not everybody contributed here, but this is somehow more or less the larger room of people in the MOCOS room here. Yeah, thank you very much. Sorry for maybe taking a little bit more time. Good.